system for our members only star parties, and it was very successful. The list for 30 people was full within 6 hours of the window opening. So we also have a wait list now. It's about 15 people on the wait list. So if anyone would like to sign up, you will be added to the wait list, and I will let you know 24 hours before the event. And all members will get an email for next month's star party when that sign up window opens. And that's all I have to announce because our star party is full for this weekend. So I will turn it over to Linda.
Okay. We always meet on the third Wednesday of every month. And so I'm going to tell you briefly about the next 2 months. On October the 19th, Dr. Dan Wilkins will be speaking to us, and he's going to tell us that we are born within a bubble of stars. The universe is big, bigger than we can comprehend, and has fascinating details on every scale. Find out how astronomy can answer how the universe evolved today and how this picture fits with a recent discovery about the history of our stellar neighborhood, 1,000 light-year wide bubble of stars in which we live. We're right in the middle of it just by chance, but we are within 1,000 light-year bubble of young stars. On November the 16th, Dr. Roger Blanford is going to be speaking to us from KIPAC, Stanford, the active social lives of big black holes. On November 16th, it's now clear that most normal galaxies have a big black hole in their nucleus. However, these black holes can interact strongly and subtly with their environment. They can acquire massive black hole partners, which become locked in an ecstatic dance before merging. And we will learn much more about these interactions from Roger Blanford on November 16th. I think I may not have mentioned that in October, Dr. Dan Wilkins of the Kavli Institute, Stanford, will be speaking to us, and Roger Blanford is with KIPAC, Stanford. We're not having a lecture in the month of December because it is just so close to the holidays when people are traveling and busy. So we'll resume again in January of the coming year. I'm very pleased to introduce tonight's speaker, Dr. Jessica Liu. She received her undergraduate degree in physics from MIT in 2000. She worked as a software engineer in Silicon Valley for 3 years before returning to academia to pursue her PhD in astronomy and astrophysics at UCLA, which was granted in 2008. After completing her PhD, she was awarded a Millikan postdoctoral fellowship in observational astronomy at Caltech. She was also an NSF Astronomy and Astrophysics postdoc fellow at the Institute for Astronomy, the University of Hawaii, Manoa, before joining the faculty there. In the summer of 2016, she joined the faculty of UC Berkeley Astronomy Department and is currently an associate professor there. She will take us on a search right now for black holes in the Milky Way, and we welcome Jessica Liu. Thank you so much.
Thank you so much for having me. It's a pleasure to come and talk to you about black holes today. And let me start my screen sharing, and then we can launch into understanding and hunting for black holes. Can you see my screen okay?
Yes, looks good.
Excellent. Okay, so I would welcome questions throughout. I can't necessarily, let's see, I can maybe try and see the chat. So if you have a question in chat, I'll definitely try to get to it. But otherwise, just shout them out. I'm happy to have much more of a discussion than a lecture here tonight. It's much more fun that way. So I'll give you just a brief introduction. First off, I am an astronomer who's both interested in observing the universe as we see it, particularly what we think of as the unobservable black holes. But I also like to help build the instruments that we use to detect them, to observe the universe. So here I'm showing what I won't have time to talk about too terribly much today, which is the Laser Guide Star Adaptive Optics System at the Keck telescopes, and they're shining up towards the very center of the Milky Way. You can see both of these lasers are pointing up to this spot in the Milky Way. If you've ever been out and seen the Milky Way yourself, you see the dark band that runs across it. That's where actually most of the stars in the Milky Way are. And the darkest part of that band is the center of the galaxy. So we'll talk about the supermassive black hole that sits there, along with the sea of stellar black holes that reside throughout the whole galaxy. Okay, but before we can launch into any discussion of black holes, we all need to get on the same page for what is a black hole. Fundamentally, a black hole is a place where our understanding of physics breaks down. Physicists like to call this a singularity. It's a place where you pack in some amount of mass, can be big or small, into zero volume. So you get infinite density. Now, we don't think this can actually work, but when it does happen in the universe, then we get a black hole. And black holes are very simple. They have very, very few properties. They have a mass, and that mass sets the scale at which the black hole becomes black. That's what we call the event horizon. And as far as we know, when you cross over the event horizon, you can no longer escape. You can try to shout, you can try to send a flashlight signal, but nothing can get out to tell someone that you're inside the black hole. So whatever goes in is essentially lost forever. We can get into the details about black hole evaporation and whatnot at the end, but for our intents and purposes, especially astrophysical black holes, a black hole is black for as long as it exists. So that's what makes black holes so mysterious and so interesting to study from a physics and astrophysics perspective. When we look out in the universe, we see two flavors of black holes. There's the ordinary black holes, which are the fate of massive stars. So a star is born, and if it's much more massive than our sun, maybe 20 or 30 times as massive as the sun, it lives its life, and then when it dies, it turns into a black hole. That death process can be very violent. As you see at the picture on the right, this is a supernova remnant. After a massive star has died, it exploded and left behind this shell of gas. So you can see it lost a lot of its mass. That's why the black hole that's produced is so much less massive than the star that began it. So these ordinary black holes are fascinating. They were first predicted by theory, sort of pen and paper math. And we think, again, this is pure speculation, we think there's somewhere between 100 million and 1 billion black holes floating in our Milky Way galaxy. That's an incredible number of objects for us to not be able to see at all. We could just turn around and over our shoulder, there's a black hole. The second flavor of black hole is a supermassive black hole. These are 1 million to 1 billion times as massive as the sun. And we think that at least one of these resides at the center of every galaxy. These were actually first found from observations. They were not predicted by theory. And our own Milky Way galaxy does indeed have a supermassive black hole. And I'll talk a little bit about how we found that black hole to begin with. So we have these two flavors of black holes, at least. There may be other more exotic ones that I'll get to later. But how do we find them? They're black. They don't emit light themselves. So how do we possibly see this thing in the universe that's out there floating that has no light? It doesn't send us any signals about how it lives its life. For all intents and purposes, these things are stellar ghosts. We have to use not direct probes, but indirect probes to actually find them. So how do we do that? The first thing we do is we can see, in quotes, these stellar ghosts. If a black hole happens to have a neighbor star, a companion, as you see here in red, and that companion happens to be very, very close to the black hole can pull off some mass. It can pull off some of the material from the outside part of the star, and it can eat it up. And as it does, this accretion process, the gas flows in through the event horizon. Just before it passes into the black hole, the gas is extremely hot. It heats up all along the way as it's collapsing into the black hole. And that extremely hot gas glows in X-rays. So that's a nice signpost for us to look for black holes. We look for things that have this accretion signature, very bright X-rays, fluctuating a lot. And then we watch and find the companion star and watch it wobble around, and we weigh it and we see that it's a big, massive, dark thing that it's orbiting, and that is surely a black hole. So that's the traditional way we've been finding black holes for the last 2 decades. Despite many decades of searching, we've only found a few dozen of these black holes, and maybe a dozen or so in the Milky Way galaxy. These days, I'm very, very excited about this. We can now hear, in double quotes, black holes. How do we hear black holes? Well, if you have 2 black holes now in a binary system very close to each other, if they orbit, eventually, if they're close enough, those orbits will shrink and shrink and shrink, and the 2 black holes will merge. When that merge happens, they send out ripples in space-time called gravitational waves. So you may have heard about LIGO and more recently Virgo and Kagra, which are these brand new I should say 5 years old now, gravitational wave detectors, brand new in the history of human civilization. So these gravitational wave detectors, for the very first time, can sense these ripples in space-time. It's an extremely challenging technical project, but they are capable of seeing or hearing the merger of these two black holes. And an example gravitational waveform is shown on the bottom here in blue and red. They're so hard to see, they build two gigantic interferometers, instruments, one in Hanford, Washington, and one in Livingston, Louisiana. And they have to verify the signal that's so faint, it has to show up in both instruments scattered very far apart to prove that indeed they saw these ripples in space-time. So we can see these black holes and we can hear them. But unfortunately, all our probes so far have been for black holes in binary systems. This is a picture, also a piece of art, but a beautiful picture showing all the black holes that we've ever discovered. So you can see the mass of the black hole is on the vertical axis. Let's see if you can see my mouse. It doesn't look like it. Okay, so the mass of the black hole is on the vertical axis. You can see that's in solar masses. So 1 is 1 times the mass of the sun. Most of the black holes, which are shown in blue and pink, are above 5 solar masses. Just a few of them a little bit less than that. And then, unfortunately, all of them are in binary. So you see each one has a little binary pair. The mergers, they merge together and become a single black hole later on. So we've got these great probes of black holes, but our sample is always limited. And I will say all of those gravitational wave black holes are in very distant galaxies. We can't use gravitational waves to see the black hole binaries in our own Milky Way, mostly because it's very rare to have an actual merger. So you have to go to distant galaxies to see one. To hear a merger. So is that it? Are we out of luck? What can we learn from what we do know with those binaries? It's pretty limited. In fact, with just the binary sample, we're still left with really, really basic questions, like what is the total number of black holes in the Milky Way? We've only found a couple dozen, so it's pretty hard to extrapolate from there and say, yes, it's 100 million, or it's 1 billion, or it's 10 billion black holes in our own Milky Way. So that's a really basic question we don't know the answer to. We also don't know exactly what kinds of stars turn into black holes. Is it 20 solar mass stars that turn into black holes, 30 solar mass stars? Is it something in between? We really don't know the answer to that. We don't know when black holes are born from the death of their star, what their masses are. So are there black holes that are very low mass, very high mass? What's the distribution? We don't actually even know how many black holes are in binaries or versus how many are single, and when will they merge? That makes it extremely hard to interpret the binary merger observations that we do have. Do they get kicked when they're born? When there's this violent explosion, does the black hole fly away? And do mysterious primordial black holes exist? These are very speculative, but perhaps during the Big Bang, these little pieces of space-time collapsed into primordial black holes that are still left over today. And do they make up some or any part of dark matter? So those are pretty fun questions. How do we answer them? To really make progress on these questions, we have to find free-floating black holes, isolated black holes, things that don't have companions. And that's where our work comes in. Fortunately for us, I told you there's lots and lots of black holes in the Milky Way. They're very plentiful especially towards the inner galaxy. If you look in towards the galactic plane of the Milky Way up in the sky, if you just hold your thumb up, that's about the size of the full moon. And inside that patch, you should be able to find a few hundred, maybe 50 to 100 black holes, right? So it's pretty easy to find. I should say you should be able. They're there, but to find them is the trick. To figure out, underneath my thumb, this is exactly where the black hole is. That's tricky. So this is all just theoretical simulations that we've done. We've made a mock Milky Way in our computer and populated it with our best knowledge of where black holes should be today, just based on how many stars there are, how stars are born and die, and then how many black holes they leave behind. Okay, so now what do we do? Well, we can use a trick to find these dark objects that are out there floating. There's no light coming from them. There's no accretion. So no signal at all, but we have one thing we can use, which is their gravity, their mass. There's this lovely effect called gravitational lensing. You're probably familiar with lensing of a different sort. You may have used your camera on your cell phone. You may have looked through a telescope or binoculars, all of which is doing lensing. Here's a little very simple evening test you can do to practice your lensing. You can get a wine glass and use the bottom of the wine glass, stick it in front of a candle or a small light bulb, and you can see the lensing. This is not gravitational lensing, just regular lensing. So the wine glass acts as a lens and it bends the light. It takes that point source of light that was coming from the candle and it turns it into a ring or into multiple images. You see in the bottom right, you can see two pictures of the candle, right? You know there's only one candle, but somehow you suddenly see two of them. So this is lensing, and gravity can do the same exact thing. So when a black hole passes in front of a background star, the background star's light can be lensed. The background star is the candle, the black hole acts as the lens. And it too can produce multiple images, just as you see here. You may be familiar with some types of lensing. You may have seen images of gravitational lensing by galaxies. So these are two gravitational lenses. The galaxy in the middle is the thing that has all the mass in front of a background, a very distant background galaxy. So on the right-hand side, you can see the four images, and the four images are a one background quasar, an accreting supermassive black hole. So it just happens to be a bright source. Think of it like the candle. And the foreground galaxy is lensing and making those four images. Really, there's only one background galaxy. So that's strong gravitational lensing. And it's this wonderful technique to use for studying the whole universe and to constrain cosmology. It doesn't help us. This is happening, but our telescopes for Milky Way black holes, our telescopes are not big enough to resolve all the images. We have to get trickier. Instead, what we're looking for is gravitational lensing that is not resolved. Instead, if I show you this image, so we're looking for a black hole that's passing in front of background stars. If we could come in really close to the black hole with a giant telescope, this is the kind of thing that we might see. In reality, it's not nearly so dramatic. So here's just the schematic view. The background star is on the left. Its photons are coming out. Its light is coming out. Those light rays get bent by the black hole's gravity and produce these multiple images. And those photons then keep traveling all the way down to our telescope. But when we take a picture, all we see is that single background star. We can't separate the two images that are made. What we do see, though, is that star gets brighter when it's being lensed, and its position on the sky shifts when it's being lensed. You could think back to the the precession of Mercury. The very first tests of general relativity, people were measuring the position of Mercury as it was going along its orbit, and they found that there was a deviation. That deviation came from gravitational lensing by the sun. So exactly the same process produces both the brightening of the background star and the shift in the position of the background star. Obviously not nearly as dramatic as Mercury's shift. Okay, so here's a little animation. Imagine we're looking out into the universe at a black hole. Here's a background star that's passing by on the left. This is what we would see if we had an infinitely large telescope. We could resolve those two images. So this is just a fun little animation to show you what happens with time. The star passes by, it gets strongly lensed, and then the lensing fades away. And if I repeat this process, if you look in the lower left and the bottom right, you can see two little plots, one showing the brightness of the star over time, and the other showing the position over time. That's what's happening to the background star as we would observe it with real telescopes, not with infinitely big telescopes. We just see the star get brighter and the position shift. At least that's what we hope to see. Okay, so now let's get a little more quantitative. Here's another animation now of some data much closer to the kind of thing we could observe on the bottom. Same exact thing. The star is passing by in red. The black hole is the orange star on this plot. It produces the multiple images in blue. You add those up. Add here, you can see you add them up, and that's what makes the flux get brighter temporarily. Now, this brightening, this photometry, unfortunately doesn't tell us anything about how big the lens is. It doesn't tell us how massive it is. But that's what we need to know. We need to know the mass of this thing to know if it's a black hole. Because unfortunately, everything with mass gravitationally lenses, not just black holes. Stars, neutron stars, white dwarfs, even planets can gravitationally lens. So how do we know that this gravitational lens that we see is actually a black hole? We have to measure its mass. So the brightness is not enough. We have to measure the position. So here's again a plot showing the position on the sky. The background source star is going by in green. You see it mostly goes in a straight line with a little tiny bit of wobble from the Earth going around the sun, what we call parallax. And then the two images are shown in yellow, this mustard color, where they go over time. So you see the two images make all kinds of weird position changes, but we can't see the two images separately. We can only see the combination of both of them. And that's what's shown in red. So the red is what we would actually measure with a telescope. The green is what's happening really in the universe, but the red is what we'd see. And this shift right here, this shift is where we get our mass information. The size of this shift tells us almost exactly what the mass of the lens is. And that is what we can use. The combination of the brightening of the star and its shift is what we need to be able to determine if we have a black hole. So here we mocked up a little simulation. This is not real data yet, to say, can we even detect this? Is this shift big enough? Well, you'll see right away that the shift is extremely small. So this is in units of milli-arc seconds, but I can put it into a unit that's maybe non-astronomers units. So that little deviation that you see, this little bump in the middle, that is equivalent to being able to measure someone blinking their eyes on the moon from the surface of the Earth. That's pretty challenging. Even if you didn't have the blurring of whatever helmet or that would be a very tough thing to see with a camera on the surface of the Earth, to be able to see somebody blinking. But that's the kind of measurement that we're trying to make. That's how far the star has to shift, and we have to be able to measure that. Okay, so now in more quantitative units, if you think about time flowing on the horizontal axis here, that shift that we have to measure in units of milli-arc seconds is on the vertical axis. And I'm showing this because I wanted you to see that the shift is biggest for black holes. Black holes we expect to have around 10 solar masses. And that shift is a little over 1 milli-arc second. We can still detect a 5 solar mass black hole, but as you get to lower mass neutron stars, regular stars, they're too small to measure. So the best astrometry that we can do from any telescope today is around 0.3 milli-arc seconds on this vertical axis. So that 0.3 line shows you right away, we could find black holes with this technique, but not much else. Okay, so we now have all our tools and techniques, and we're ready to go hunting for black holes. So the problem is that this gravitational lensing requires a chance alignment between the black hole and the background star. That's a pretty rare event. It's also very hard to measure. So we have to know somehow creatively where to look to maximize our chance of finding a black hole. So here's our little animation of where we think the best place to look is. This is showing the top-down view of the Milky Way. Obviously, we can't do this in real life, but here we are on Earth. The best place to look is towards a place where there's lots of background stars. So that tends to be towards the center of the Milky Way. There's lots and lots of stars. It's where there are the most stars. So we can look towards the center of the Milky Way and we wait for an intervening black hole to pass by. So we like to look at this region of the sky. We look towards the Milky Way and we stare at the patch of the sky again and again and again with dedicated surveys that are just looking at the Milky Way and a little bit of the galactic plane. That's what's shown in the colors here. This is the survey patch for a survey called OGLE, which is just dedicated to finding gravitational lensing events. And they stare at this patch of the sky every single night without fail for as long as they can all year round, unless COVID hits. And then they've been down, unfortunately, for the past 2.5 years, and they've just come back up now. So we've definitely been impacted by COVID in astronomy, even though you might think we are just sitting in front of our computers every day. We really do miss having this lovely data set. So staring at the sky, this patch, they're monitoring millions, tens of millions, hundreds of millions of stars every single night and looking for these rare gravitational lensing events that occur. Here's a few example light curves of the kind of data that we're getting from these surveys. They give us the brightness measurements alone. These telescopes are small telescopes with big fields of view. They're not able to measure the positions very well, not well enough to do the experiment that I told you about, but they can do the photometry, the brightening. So here's 4 different stars that they found were microlensing. These stars, you see, they're flat for a long time and then they rise and then they fade away. That's exactly what we think happens with microlensing. So this is just a random suite of 4 targets that show this microlensing behavior. So what we do is we go through their catalog of all their microlensing events as they're happening in real time. And we pick just a few out that we think might be good black hole candidates. And we then start to use the Keck telescopes, which is on my background screen. If you can see me, it's my background photo. That's the Keck Observatory. So the Keck telescopes are equipped with adaptive optics that can defeat the blurring of the Earth's atmosphere and give you very sharp images. And that's how we get our precise positions. But we have to be very careful. Which of the 1,000 microlensing events that are found each year, which ones might have black holes? So we turn to our mock Milky Way simulations to, again, tell us which ones we should look for. So the microlensing events in our mock simulation, we plot them up and we look at their properties. For the brightening, how long is the microlensing event? What's its duration? That's on the horizontal axis. We can also then say, okay, which ones are going to have the biggest position offset signal, the astrometric signal? That's on the vertical axis. And then you can see from our simulation where all the points fall. And the black holes like to fall on the long duration end. This is in days, so most of the black hole microlensing events take 100 days to go up and 100 days to come down again. So these are not quick bursters. These are not explosive. You might miss it if you don't look carefully and every day for a long time. So that's the kind of microlensing events that we're looking for. You can see there's not a lot of them compared to the bulk of them that are happening from stars down at 10 days. But we know we can pick out these long duration events and they're much, much more likely to be black holes. From the current surveys, there are really only 10 or so good candidates found from the photometry surveys, things like OGLE. And so those are the ones we would want to concentrate our time on. Once we've picked those targets, we use Keck, as I mentioned before, or the Hubble Space Telescope to start making measurements of the position of the object. So we just start taking pictures. That's all it is. We take pictures of these microlensing stars. They're in the middle of being lensed. We kind of try to start monitoring at the peak. And then we have to measure them and measure them and measure them for years, right? These microlensing events take a long time, hundreds of days. And so we just have to wait and be patient. We take about somewhere between 12 and 20 pictures over 5 or 6 years. And we use all of those measurements to look for that positional offset, that positional deviation. So I thought I'd go through a couple candidates. We first started this experiment way back in 2011. I was still a postdoc at Caltech, and I was thinking about, oh, I think we can do this project now. It didn't used to be technically feasible, technically possible. But I had just come from working with Professor Andrea Ghez at UCLA on Galactic Center, trying to use the measurements of the positions of stars orbiting to find a supermassive black hole at the Galactic Center. And we used exactly the same techniques. We needed to measure stars' positions extremely precisely, and we needed to do it at the few tenths of a milliarc second level, which is exactly what we needed for this black holes program. So I launched as a postdoc this program to study a few candidates with this astrometry method, this position method. Now, it was hard work. We did get data, but unfortunately, you can see this is real data now. It looks pretty much like a straight line. Not much there. So the very first sample of 3 candidates that we did was a big old negative result. No black holes. But importantly, we used this data, the photometry on the bottom, the brightening, and the astrometry, the positions on the top, to show that we could tell what the mass of the lens was. So on the lower left, you can see this is our, what we call probability distribution for the masses. Everything under the curve is allowed. And you can see the allowed masses are small. They're about a solar mass, definitely not more than 1.4 solar masses. That's not a black hole. That's just going to be a run-of-the-mill star. Maybe if we're lucky, it might have been a white dwarf. So that was great. At least we could prove that the technique worked, even if we didn't find a black hole on our first pass. So then we started the next batch. We started using OGLE data, this survey, to find the microlensing events. And we also started monitoring a new batch, both with Keck and another set with a Hubble Space Telescope. The Hubble Space Telescope data, there were 5 black hole candidates that were monitored with Hubble towards the center of the galaxy. And in the upper right here, you can see one of them. And I think this is a movie that should play. So this is showing from the OGLE survey, it's showing their patch of the sky and their images that they were taking. And they saw this, if I play it again, oops, sorry, let me check that again. You can see the star flares up and then fades away. That's their real data on the top in those images. So that was a sure sign of a microlensing event. And about at the peak is when Hubble started to observe it. Okay, so this is what Hubble observed. There's the measurements flowing by. You can see the measurements are taking 6, 7, 8, 9, 10 years. 10 years of data. This is a long program. You have to be very patient to work on this project. But you can also see, it's a little hard to tell from here, the stars, the background stars whizzing by pretty quickly at many milliarc seconds per year. So it's a little hard to see. Is it just a straight line or does it have an offset in it? That's what we're after, right? That offset. So let me remove the main straight line motion and then you can see a little easier. So now on the top is the brightening, the photometry. That one's pretty easy to see. On the bottom is positions. So in the 2 panels, we're showing the positions in right ascension or east-west as a function of time in days. And on the right is the position in north-south declination as a function of time. If the star was moving in a straight line, it should all the points should be at 0 on both of those plots. And what you see is that in fact, the points do not look like they sit on 0 the whole time. Even with measurement errors, which are the little error bars that you see, you can see that the points do sit significantly off of that straight dashed dotted line. That's what we were looking for. It's exactly what we had hoped to find. We see a significant positional offset. And when we fit both the astrometry and the photometry combined, we can make a model. And that's what's shown in black. And that model says that we have either a 3.7 solar mass black hole or a 2.7 solar mass neutron star. Now, why do we get 2 answers? This is a bit tricky. The photometry data on the top and the astrometry data, positions on the bottom, they prefer 2 slightly different solutions. And we don't yet know why. This is the current puzzle that we're working on. What's wrong or what's oversimplified in our model? What more complicated things do we need to add to get those 2 to agree with each other? That's what we're currently working on, and it will tell us the answer, which of these 2 answers is correct. Do we really have a black hole, or do we have a slightly heavy neutron star? Either way, both of these events are exciting because we've never been able to find a dark object through microlensing before. And this is the first time we've been able to do that definitively. And we think this shows us that we can do this quite a bit for many more black holes to come in the future. So this one event was went through a series of press releases. You may have heard about it in the spring. We were very excited. Another team has been working on the same object from Space Telescope Science Institute. What's great is that both teams agree that we found a dark object with gravitational lensing. We're still arguing about what the mass is and whether it's definitively a black hole or not. But stay tuned. There's going to be more papers coming out soon. But the one object is not the real. This doesn't answer the questions that we posed earlier. If you remember, how many black holes are in the Milky Way? What are their mass distribution? Do they get kicks? All those really fun astrophysical questions that tell us something about the universe and how stars are born and live and die. We can't do that with just one object. We have to have a sample. So we take the whole sample of all the targets that we've ever looked at, which is a grand total of 6 so far, not very many. And we can compare what we've observed to our mock Milky Way simulations that I showed you earlier. So that's what these figures are showing. So we take our mock Milky Way and we look at the duration of microlensing versus the shape of the microlensing curve. We can look at the positional offset that we measure versus that shape parameter. And what's really fun about this figure is you can see right away that the targets that we tried with Hubble, at least, were in a zone where we weren't really very likely to find black holes anyways. So the one target that did end up being a black hole is called OB 110462. It's the one that's in black and purple. Those are the two solutions. And you can see those, they don't quite fall into the black hole cloud. They're kind of on the edge. And then most of the other targets were solidly in the stars cloud. So that tells us right away that we just sort of had bad luck, or we really need to choose better the targets that we're going to look at. Not just that they have long duration, we need to go to even longer durations, or we need to look for light curves that have this shape parameter, which we call the microlensing parallax, to have that to be a low number. So that's what we're doing. We're advancing our choice, our selection of these gravitational lensing events to try to up our chances of finding black holes. Even without all of that, we can take these to turn it around and immediately test how many black holes are in the Milky Way. And so far, with our limit of these six objects that we've studied, one of which was a black hole, we can say that that number, that 1 out of 6, is consistent with about 200 million black holes being in the Milky Way. If you take that number and say there's 200 over the whole Milky Way, you can ask, where's the closest black hole likely to be? Probably within 80 light years of Earth. So the nearest star is probably a few light years away. So the nearest black hole is significantly further than nearby stars, but it's not that far away. So 80 light years is definitely within that bubble of young stars that you're going to hear about next time around. Okay, so the other interesting thing is that we can look at what we thought our success rate would be for finding black holes in the sample. And so we again turned to our simulations. We first simulated up a mock Milky Way with only black holes in single systems. And then we made a Milky Way model with all black holes in binaries to test the two ends. And it looks like, so far at least, again, pretty big error bars here, but that the number of black holes we found compared to our sample is more in line with most black holes being singles rather than being with companions. So I don't know what happens if they all got divorced at some point, because most massive stars are born in binaries, but somehow these black holes end up as singles predominantly. Maybe they get kicks, or maybe at the end of a massive star's life, when it loses all its mass, the two float away from each other. And so that might be why the black holes are mostly single today. All right, so I'm coming towards the end. I want to leave lots of time for fun black hole questions. But I thought I'd close with a little bit about what our next step is in our search for black holes in the Milky Way. So the first thing is that photometry, the brightening, the just searching for microlensing events. There's lots of ways that we can do better with photometry. So we can get out of just looking at the center of the Milky Way and try to get out into the whole, covering the entire galactic plane. The more stars we look at, the more likely we are to find microlensing events and hopefully then black holes. We can also do better with our astrometry, our position measurements. We're working on improving our ability to measure the positions of stars. We do this right now through our telescopes and through our adaptive optic systems, and that's a whole series of optics, and they all have distortions and aberrations and warp our images a little, and we have to undo all of that. So we're working on improving our ability to calibrate out all of the instrumental signatures, all their distortions, so we can get back to the true positions of the stars on the sky. So that entails actually building new pieces of hardware and taking it up and installing it on the telescope and playing around with it, and then taking calibration data. And then once we do that, we can apply it to all the observations we get on the sky. We're excited about new telescopes that are coming. So JWST, James Webb Space Telescope, is obviously flying now and very exciting, but we're not really sure how well it's going to do astrometry just yet. So we're having to be patient with that test. One mission that's coming up that we're super excited about is called the Nancy Grace Roman Survey Telescope. And this is a space telescope that is like a Hubble, but its field of view is many, 100 times, well, maybe not quite 150 times bigger than the Hubble Space Telescope. So yeah, you can see its field of view here compared to the HST, which is in yellow, or even JWST, which is in the bottom yellow. What's neat about this big field of view is that the telescope was designed to do surveys. So just like I mentioned, OGLE, a small ground-based telescope that's staring at the galactic bulge every day again and again, Roman is going to do the same thing, but it's going to do it from space instead of on the ground, which means its images are incredibly sharp relative to the ground-based turbulent seeing limited images that we typically get. So Roman is going to do a microlensing survey. It's nominally aimed at detecting exoplanets, but we hope to twist their arm a little and convince them to look for black holes too, with just a little bit of modification of that survey. And then finally, we're extremely excited about the next generation of very large ground-based telescopes. So I mentioned the Keck telescopes. Those are 10 meters in diameter on the summit of Mauna Kea in Hawaii. That's one of our biggest ground-based telescopes today. And when you put an adaptive optics system on it, it can give you diffraction limited images, very, very sharp images, some of the sharpest images of the universe that we can make. But if you build the next generation 30-meter telescope, which is 3 times bigger in diameter, 10 times in area, it can make sharper images than anything we can see today, even to the point that if a close by black hole were to gravitationally lens a star, we could start to resolve those multiple images. Remember, I said the most multiple images, we can't see them with our big telescopes, but with a 30-meter, we could start to see it. And even without that, it will be able to do amazing astrometric measurements, position measurements, much more precisely than we can today. So we're extremely excited about that. And just to give you a hint of what that looks like, here's a picture of not a stellar mass black hole, but a supermassive black hole with all its stars orbiting. This is at the galactic center. And this is a little simulation showing what we can do today versus what we can eventually do with the 30-meter telescope. And I'm going to start this animation. You can already see the spatial resolution is incredibly improved. And then as the stars move, you can see how many more stars you can see, how much more precisely you can get the orbits of all of these stars that are now would now become measurable with a much, much bigger telescope than what we're currently working with. So we dream about this, we astronomers dream about this day when we'll be able to take such a facility and point at our best black hole candidates and watch them and see if we can see the multiple images and watch their tracks on the sky. And lastly, I've talked a lot about trying to find single black holes, but I like binaries too. So we also like to search for binary black holes. My fun project for many students right now is to look for baby black holes next to the supermassive black hole at the center of the galaxy. So black holes all around. So we do in fact think that there should be a swarm of stellar mass black holes surrounding the supermassive black hole at the galactic center. And so we're looking for them. And one signature that we could use to find them is if they have a companion star going around it, we could watch the companion star wobble up and down due to the presence of its stellar mass black hole companion. We think we see the first hints of this at the galactic center, but this is extremely preliminary. We're excited, but we have to confirm it. And so we are embarking on our first James Webb Space Telescope images and spectra of the galactic center to test exactly this. And we just got the data this month. So we've been diving into that. It's been pretty fun. So all in all, we can see black holes, we can hear black holes, and now I think we can watch black holes and their gravity lens, the background companions, to find free-floating black holes. My hope is that 10 years from now, we'll have a fantastic census of black holes in the Milky Way, both in binaries and singles, and we'll have answered quite a few of those questions that I first posed. So I'm really looking forward. I think it's a renaissance of black hole research at the moment, as I see from your talk schedule. I hope you think so too. So I'd like to thank all the amazing undergraduate, graduate, and postdoctoral students and postdocs that I work with in my research group, along with many, many collaborators from around the world. All their names are listed here, and I'm happy to take questions.
Wonderful. Thank you very much. Yes, anyone can jump in and ask a question or click the raise your hand button or type it in the chat and I will read it aloud. And we have one already from Philippe. Does this suggest that stellar black holes, at least those you are looking for, have no accretion disks? And that was asked a little earlier in the lecture. So
Yes, right. So accretion disks have to be populated with gas. That gas has to come from somewhere. When a black hole's in a binary, a close compact binary with another star, the gas comes from the star. If it's just a free floating black hole out there in space, it doesn't have a lot of gas to accrete. Now, there are clouds of gas. So maybe if it happens to pass through a molecular cloud, you might get a little bit of accretion. But all in all, the accretion that we expect from a free floating black hole is extremely, extremely low. Good question.
thank you. Thank you. I was wondering, did you touch on how long we think it takes for a black hole to form? Like it's not like an event that like we would just see in a day, right? It's a very slow process.
So the formation of stellar mass black holes is extremely quick. In fact, it happens when a massive star dies. So imagine a star 20 or 30 times as massive as the sun, or maybe 100 times as massive as the sun. It's gone through its life. It went through most of its life burning hydrogen. Then the hydrogen fusion stopped and it turned into helium burning. It may have puffed up and become a giant for a while and blew off some of its mass. But at some point, when hydrogen fuses to helium, fuses to carbon, fuses to nitrogen, oxygen, on and up until it gets to iron, at some point, fusion can no longer sustain the star. And at that point, the star's fusion shuts off, and then there's nothing holding it up against its own gravity, and it collapses. That collapse is extremely violent. It happens in a matter of a minute.
Wow.
And the collapse actually causes a ricochet, which can then produce a supernova explosion. And so, the supernova explosion is extremely rapid. It rises and then it fades away. It can be when we see it at the optical wavelengths, it happens to fade. It takes many months to fade away because there's some gas that's left over that is slowly cooling off. But the black hole is formed extremely quickly in a matter of just a few seconds.
And that's something we've been able to observe, that quick formation, that sudden collapse.
So that's right. So we observe supernovae all the time.
Amazing.
One of the really interesting things about research right now is that we're not sure whether those supernovae are ever producing black holes or if they're always producing neutron stars. So there's a running theory that's going around now, which is perhaps when the most massive stars die, they collapse, but they don't get that bounce and produce a supernova. They collapse and then they just disappear, and most of the mass goes into the black hole. So you could just get a star that goes quiet, goes away, rather than a star that goes boom when the black hole is made. So whether supernovas produce neutron stars or black holes or both is an active area of research, and we observe supernovae all over the universe. The question is whether we're really observing black hole formation or whether we have to go around looking for disappearing stars to find black hole formation for real.
We have a question from Xander asking, what does WD mean? And I don't recall seeing WD.
That was in, let's see, hold on, let me go backwards. Whoops, one moment. I think that was in one of these plots.
Oh, yes, there it is.
Right, so greens are all the stars. WD here is white dwarf, and NS is neutron star, and BH is black hole.
Very good. Philippe asks a question, do we have a range of the sort of velocities of black holes as they move through space?
Yep, all the black holes are not still. In fact, none of the stars are either. Our whole Milky Way is kind of moving around. The disk of the Milky Way rotates. But even within that rotation, there's lots of dancing around it. And so, there are a range of velocities that we think are there. We can obviously measure the stars' velocities, but we can't measure easily the black hole's velocities. So we don't know if the black holes are moving around with the same velocities as the stars, or maybe the black holes are a little faster, or maybe they're a little slower. That's one of the things we hope to measure with this microlensing. We actually get a constraint on the black hole's velocity too. So we're really looking forward to getting a big sample and telling you whether black holes are more dynamic, dancing around faster than the stars, in which case maybe they got kicks during their formation.
Okay. Okay. Um, I was wondering, we commonly see in the news that they'll say the first photograph of a black hole. And I always think to myself, that's probably not a real photograph. It's probably some other kind of image collection. Can you explain what these images, what they are?
Yep. So most of what you've heard about is probably from the Event Horizon Telescope. So that's it's a set of telescopes that work at radio wavelengths or submillimeter wavelengths. We're usually looking in the optical and the infrared here. So they're looking at radio wavelengths, and what they're really imaging is not the black hole itself, but that accretion that's happening around the black hole. And the reason it looks like a ring with a dark hole in the middle is that this accretion disk, which is usually an edge-on disk, edge on to us, gets gravitationally lensed by the black hole. And so the light from the accretion disk gets all warped around the black hole and comes out as this donut-looking shape, or this bagel-looking shape. So yeah, what you're really seeing is the accretion disk that's been gravitationally lensed. And then the hole in the middle is the shadow or the silhouette of the black hole. So it's a little bit like a ghost. It's, you have a bright light behind you and all you see is kind of the outline. The
event horizon is sort of.
You're not actually seeing the event horizon. You're just seeing, actually it stands out from the event horizon by a factor of a few. So that silhouette or shadow, it's the light, it's the shadow left by the light coming around the black hole from the accretion disk, and it leaves this kind of shadowy shape that's a little bit bigger than the event horizon. But they can use it to tell you where the event horizon is.
And these are the pictures of the accretion disks are actually like the visible light spectra. They're
all taken at submillimeter and radio wavelengths.
Oh, okay.
And unfortunately, we don't have big enough telescopes, single dish telescopes, to truly make the image that you see. So that's an image that's been reconstructed from a pretty complicated data set that involves several small telescopes scattered around the world, all looking at the same point in the sky at the same time. And then they perform what's called interferometry. They reconstruct the image from the measurements they take from those telescopes. So there's a lot of really complicated modeling that goes into making those pictures. But to be confident, they have separate teams that work on making the pictures from the same data to verify that what they saw was the same for everyone, because it really is a heavily processed, heavily reconstructed image.
Yes. We've got another question coming in. You've talked about the formation and velocity of black holes. Is there any data about the lifetime of a black hole?
Yeah, that's an excellent question. It's extremely tough for us to envision even theoretically, ever figuring out how to age date a black hole. So the black hole alone is such a simple, pure system. It just has mass. Maybe we can measure its spin someday, but there's nothing else about it that tells us how old it is, when it was born, or even how it formed, what it looked like before it became a black hole. So I think it would be quite challenging to figure out the heritage, the age, or the lifetime of a black hole as a result. Yeah, I think that's a tough one. Maybe someday we could try to associate black holes with particular star clusters that are of a certain age. That might help, but we'll have to get way far down the line and really be able to find isolated black holes with great regularity to find that.
Question from Xander. What is a ringularity?
I don't know what a ringularity is. I've heard of a singularity.
I think it might have been regularity or singularity got mixed together.
Yeah, Xander, if you've heard of this term, I'm curious where you've heard it. There is something called a ring down. I've never heard of a ringularity, but that's a fun term if somebody's coined it. There is, when two black holes merge and they produce these gravitational waves, after the merger happens, for a short period of time, there's a little ripple in space-time that still persists. It's the black hole's kind of settling down into its final state. And so that we commonly call it a ring down.
I think I know what a ringularity is. I think it's like, so I think there's no such thing as a singularity. There's only ringularities, because ringularities are like singularities but in a ring. Like a circle.
I see. I think
Really
that
fast spinning black holes should have a singularity.
It is a term.
I-
I've just found it on the internet. Yeah.
very cool.
Oh,
Yeah, so you'll have to ask your local string theorist about ringularities then. These probably involve quantum theories of gravity that are still far from being tested observationally. So me as an observational astronomer out looking out in the universe,
Yeah,
we'd be hard pressed to ever find this, but a string theorist might be able to tell you.
Yeah, I learned it from a YouTube video. The channel is Universe in a Nutshell.
Excellent. Thanks
Oh,
so
I've
much.
heard of that one. I've heard of that one. It's a good one. I was impressed by we're dealing with milli arc seconds. That seems so just inconceivably tiny.
It is quite small.
I just
It's
wanted to
almost
appreciate
hard to imagine.
that.
Yeah. Yeah, if you're an amateur astronomer, you're used to, okay, the full moons, what, half a degree? Maybe when you're taking pictures, the stars that you see, you might have a spatial resolution of a few arc seconds, 10 arc seconds in San Francisco, I would guess.
Mhm.
And so, yeah, we're down at the milli arc second, 1/1000th of an arc second level. In fact, we have to do better than that. We have to do 3 to 10 times better than a milli arc second in our position measurements
It's
to see these black
inconceivable.
holes.
Oh, we have another question here. Is there anything approaching a scientific consensus around what the internal structure of black holes might be?
Not yet. So maybe you can ask Xander about ringularities, but my impression is that the fields of quantum gravity are still extremely new, and there's some really fantastically promising theories, but they're still working at the level of coming up with a solid enough theory to be tested. And so that's where we would really begin to understand the internal structure of the black hole. As far as we're concerned, it looks like it's still infinite mass in zero volume. Sum of mass in zero volume, so infinite density. If they have some internal structure, it's extremely compact, but exactly how compact, I think, is going to be hard for us to probe on astrophysical black holes. Even gravitational wave mergers, the most of the action of the merger is happening kind of on larger scales than what we think that singularity is. And so, yeah, I think we're pretty far off. Maybe someday with the LISA telescope, which is it's actually a formation flying interferometer LIGO in space, that might be able to sense gravitational wave signals precisely enough to start to test equations of state of matter at the densities that we care about for neutron stars and black holes. So I think we're quite a ways off, but maybe on the theory side and maybe in some lab tests, if people can make micro black holes or something in labs on Earth, they could start to test these kinds of things.
And the LISA is it's still in development?
It's still in development. It is funded by the European Space Agency, and it was one of the top recommendations of astronomers in the US is decadal review that just came out last year. It was last year. So LISA is definitely on everyone's map and is being planned and designed currently. But it still needs full funding and needs to be built. So it's still a little ways out there, maybe a decade out there.
Mm.
I have a question. Can you hear me?
Yes, we do.
Yep.
Okay. Given that black holes have a range of velocities and there's so many of them, if they get near a solar system, would they have an effect on individual items in a solar system? I would think what I understood about black holes that it would affect them.
Yeah, that's a great question. So they have a similar effect as if a star would pass by another solar system. So if you're outside the event horizon, the presence of the black hole doesn't do terribly too much to you unless you get really, really close to the event horizon. But remember, black holes, although they're massive, their event horizons are extremely small. In fact, a typical stellar mass black hole, its event horizon is going to be smaller than the island of Manhattan. So this is a tiny little thing that's whizzing through. You have to get that close to really start to feel the strong tidal forces and to have any danger of falling in, for instance. Now, you wouldn't see nothing, Most commonly, what would probably happen is a black hole passes by a solar system. It might disrupt the orbits of the planets enough to kick the planet away or to kick the planet into its star. So yeah, you can disrupt solar systems with black holes if they get close enough. But the number of black holes out there is much, much smaller than the number of stars. So you're more likely to disrupt solar systems from other stars rather than black holes.
We have a question from Philippe. If a stellar BH that is 10 SM occupies a nearly infinitely small volume, how can a BH with 60 B SM also occupy a similarly infinitely small volume?
Yes, this is why we call it a singularity, because in theory it occurs, at least in the math, but we know that almost certainly physically it's just a breakdown in our understanding of physics. So singularities are really just a signpost for we need to do more work here. And so that's what quantum theories of gravity are trying to do. They're trying to figure out it's probably not an infinitely small volume. It's probably a finite volume. And we need to figure out what that volume is and what the internal structure is. So that's exactly what theorists are trying to get at right now. Good night, Xander. Thanks so much for coming to the talk.
Well, we're at the top of our next hour here. I'm going to say last call for questions. Anyone? And thank you for joining us, everyone. Thanks very much for coming. Thank you to our guest, Jessica Liu.
Thank you, Jessica. I'm so pleased that you have spoken to us tonight. Well, much to think about, and I'm so happy that this presentation has been recorded in the lecture archive, so people can refresh their memories and look at it again and again. Thank you so much for that.
Thank you all. And if you're interested in learning more about black holes or you have other questions, feel free to reach out or come and visit us at Berkeley.
Wonderful. Well, thanks again. Thanks, everyone. And we hope to see you next month.
Thank you. Good night.
Thank you. Thank you very much.
Bye-bye.